Okay, AP Stats. I'm going to I'm going to walk through the problems I assigned for review last week. So, first one, arsenic is a naturally occurring chemical that can enter groundwater through eroding granite or from a burned forest. A health organization recommends drinking water should contain no more than 10 parts per billion of arsenic. A company produces filters to clean arsenic from private wells that could be affected by the groundwater. The company wants to investigate the effectiveness of a new filter compared to that of an old filter. They will test the filters on a field that is bordered on one side by a granite ledge and on the other by a burned forest. The field is divided into eight square plots of equal size, and a well to collect groundwater is drilled in the center of each plot. One filter will be used in each well. The company will use 4 of each type of filter to conduct the investigation, and a randomized block design will be used. So the first question is, assuming that there is a difference in the effectiveness of the two filters, under what conditions will a randomized block design be better for detecting than the difference than a completely randomized design? So they're asking a fairly straightforward question. Why would you want to use a block design instead of a completely randomized design? So if one filter is better than the other, it says that arsenic can be seeped into the ground from a granite that's eroding or from a burned forest. But if they seep in at different rates, then we would want to make sure to block by location. Meaning, if we just did a completely randomized design, there's always the chance that all these top wells closer to the granite ledge get filter 1 or the new filter, and all of these get the old filter just by random chance. Well, in that case, if the burned forest is emitting more arsenic than the eroding granite ledge, that's going to bias the results and not necessarily tell us what we need to know. It may just seem like the old filter is better when really the new filter is better. So let's word this. I'm going to say, if there is a difference in the rate that arsenic enters the water table, and I'll just say generally by location, right? Okay, by number, what wells would be identify the wells by number that would be included in each block. So I'll just say block 1 is going to be the wells on top, so that's wells 1, 2, 3, and 4. And we'll say block 2 is wells 5, 6, 7, and 8. Okay, so part C. Now we're going to actually describe how to assign the filters to wells in this randomized block design. So remember, the way a block design works is that we're going to want to randomly assign, in our case, 4 filters to each block, but you're going to use 2 new and 2 old. And that way you're guaranteeing that each block is testing new filters and old filters. And what we're assuming here is that there's a difference in the seepage of arsenic from granite and burned forest. All right, so I think the easiest way to do this is I'll go, okay, write 1, 2, 3, and 4 on separate equal sized pieces of paper place them in a hat. And mix. Select 2 pieces. These wells will receive new filters. The remaining will receive old filters. And then we're just going to say apply the same system to block 2. All right. All right, great. Let's jump to question 2. So this is a probability one. And it says, for each day that Sasha travels to work, the probability that she will experience a delay due to traffic is 0.2. Each day can be considered independent of the other 2 days. For the next 21 days that Sasha travels to work, what is the probability that Sasha will experience a delay due to traffic on at least 3 of the days? All right, so there are a couple things I'm going to note here. First of all, this is a binomial setting. And so it's a binomial setting. Remember, there are a fixed number of trials, which is 21. There's a fixed probability of success. In this case, we're considering success experience a delay due to traffic, and that's 0.2. The trials are independent. It states that, right? And the probability of success remains the same for each trial. So still 0.2 or 20% chance of being late due to traffic. All right, and it says, so what is the probability that Sasha will experience a delay due to traffic on at least 3 of the days? So I'm gonna make myself a variable here just to make my notation a little easier. X is gonna be the number of delays Sasha has. So what I'm looking for the probability that X, so at least 3 of the days, is greater than or equal to 3. And because my calculator has a command called binom CDF, but binom CDF only works with inequalities in the other direction, right? It only works less than or equal to. I'm going to use the complement rule here, and I'm going to say that, okay, that's equivalent to saying 1 minus the probability that X is less than or equal to 2. So if you wanted to think about it verbally, the probability that she's late at least 3 of the 21 days is the same as saying the complement of the probability that she's late 2 or less of the days. All right, and this will translate to 1 minus, I'm going to go binom CDF. Remember the notation is N, so fixed number of trials, 21. P, probability of success is 0.2. And X, in our case, is 2. So we can pop that into our calculator. And you can find that in distribution. So that's second vars. It's pretty far down there. Binom CDF. There we go. So trials 21, P is 0.2, X is 2. We'll paste that. And then you know what I need to do is 1 minus that answer. So we get about 0.821. All right, and that's it. Okay, so what is the probability B? What is the probability that Sasha's first delay due to traffic will occur after the 5th day of work? So we can kind of restate that. I'm going to restate that this way. That's the same question as saying what is the probability of no delays for the first 5 days? And the idea here is that, okay, that means the first 5 days are no delays. Well, what is the probability of not being delayed? Well, it's the complement of the probability of being delayed. So it's 0.8. And I'm just going to multiply that by itself 5 times. Or 0.8 to the 5th, right? And that comes out to about 0.066. Okay, consider a random sample of the 21 days that Sasha will travel to work. For the proportion of those days that she will experience a delay due to traffic, is the sampling distribution of the sample proportion approximately normal? Justify your answer. So here we just need to check one condition, and that's our normality condition. That's large counts. And large counts for a sample proportion to be approximately normal is n times p hat has to be greater than or equal to 10, and n times 1 minus p hat has to be greater than or equal to 10. If either of those is not the case, then we cannot assume normality. So in this case, that would be 21 times 0.2, which is 4.2, which is less than 10. So no, we cannot assume normality. All right, that's it for number 2. Okay, moving on to question 3 here. 34 college students were asked how much money they spent on textbooks for the current semester. The responses are shown in the following stem plot. And then we're given a key where a stem of 1 and a leaf of 2 corresponds to $120. So describe a procedure for identifying potential outliers and use this procedure to decide whether there are outliers among the responses for your money for the money spent on textbooks. So generally the rule of thumb we use for outliers is it's the 1.5 times the IQR, the interquartile range, which is Q1 minus Q3. And the way you do that is we're going to take whatever Q1 is and we're going to subtract from that 1.5 times the IQR. Whatever that number is the boundary for outliers. If there's any data that's lower than it, we'll consider it an outlier. And then we'll take Q3 and we'll add 1.5 times the IQR. And if there is any data in our set above that boundary, we'll consider it to be an outlier. All right, so for us, I think the easiest way to do this, it's a data set that has 34 pieces of data in it. I'm gonna throw them in my calculator because that'll quickly calculate like the quartiles for me, make it a little easier on us. So I went ahead and preloaded that data into my calculator. So that's all in list 1. And now I'm just gonna go to stat, calc, and I'm just going to run one variable stats on that. I'm going to tell it list 1, and then just tell it to calculate. And then we can scroll down to see. All right, so we have Q1 is 180. Q3 is 390. All right, so 390 minus 180 will give us our IQR. 390 minus 180 is 210. All right, so let's go back over to our question prompt and take a look at what we're working with. So Q1 was 180, Q3 was 390. So 180 minus 1.5 times 210. All right, so real quick, I'm just going to throw that in my calculator. 180 minus 1.5 times 210 is negative 135. And then for Q3, we'll do 390 plus 1.5 times 210. We get 705. And so what we're going to say is this for our final answers: no low outliers. But there is one, that stem of 8 and that leaf of 1 tells us that there is one high outlier at $810. All right, so based on the STEM plot, write a few sentences describing the distribution of money spent on textbooks for the 34 students. And so what we want to remember here is our acronym SOX. Remember, that's shape, center, spread, and outliers. And so I'll write up a couple quick sentences. Okay, so I said the distribution of the amount of money students spend on textbooks is unimodal and skewed right. It has a median of $285 and ranges from $120 to $810. The largest observation is a possible outlier. So I hit everything in there, right? I hit shape, I hit center, that's the median, I hit spread with the ranges, and I discussed that 810 is a possible outlier. Okay, looking at the last question for last week's AP review. It says, River Run Campground has sites for people to use for camping. The sites can be reserved for a certain number of days to help with the cleaning and maintenance, and the campground requests an exit time of 9 a.m. on the last reservation, on the last day of the reservation. To estimate the typical time, the manager of River Run selects a random sample of 60 sites. Of the selected sites, 40 were reserved by people without young children and 20 were reserved by people with young children. The following histograms summarize the exit time recorded as minutes relative to 9 a.m. For example, an exit time of 9:30 a.m. is 30 minutes relative to an exit of 9 a.m. Each interval contains possible values from the left endpoint up to but not including the right endpoint. So we'll consider those histograms. And one will say, how many of the 60 sites had an exit time before 8:30 a.m.? So we're looking for negative values that are less than negative 30 because this is all relative to 9 a.m., so none with young children. And we're only looking at these two bars of our histogram. And each one of these vertical increments is 1, so it looks like there's a total of 3. So I'm going to say 3 sites. How many of the 60 sites had an exit time of 11 a.m. or later? All right, so relative to 9, 11 is 120 minutes, right? 2 hours. So it looks like people without young children, that would be these. And there are 4 plus 1, so 5 of those. And people with young children, there are these. So 2 plus 1, so 3 of those. So total of 8. Oops. So 8 sites. All right, compare the distributions of exit times for those with young children and those without young children. All right, so I'm going to pause the record. I'll write this in and then explain it. Okay. So I said the distribution of exit times for campers without young children is skewed left, while those with young children is symmetric. The distribution of exit times is more spread out for campers without young children, the largest possible range being 210 compared to that of 105 minutes for campers with young children. Campers without young children tend to leave earlier than those with young children. The median exit time for those without young children is between 10 and 10:15, whereas the median time for those with young children is between 10:30 and 10:45. Okay, so it's basically still that SOX acronym, but we want to make sure we use comparative language for each one if possible. So you can compare shape, not directly, you can just kind of describe the shape separately. But you can compare things like center and spread, which one's larger, which one's smaller, etc. Last part is based on the histogram, what is a reasonable estimate of the median exit time for the random sample of 60 sites? Explain your reasoning. Well, there's 60 sites, so if we order them, the median has to be the average between the 30th and 31st observation if we ordered them, right? So let's go back and see if we can figure out what the 30th and 31st observations would be. So these really don't catch up until we get to 45 minutes over here. So if we're thinking about them in order, I'm going to go up to 45. I'm going to count off. So we have 2 observations. I'm just going to number these cumulatively. So 2 add 1 is 3, add 2 is 5, add 2 is 7, add 2 is 9, add 3 is 12, add 3 is 15. Okay, so between 45 to 60, we're going to have 2 more here and 2 more from this side as well. So 2 plus 2 is 4, 15 plus 4 is 19 in that category. And then 60 to 75 on the left-hand side without children, we have 4. And on the right-hand side, we have 3, so 19 plus 7 is 26. And 75 to 90, we have 4 here, and we have 75 to 94 here. So 4 plus 4 is 8, so this is 34, right? So the median is going to be somewhere within this interval, somewhere in between. Actually, I can narrow it down even more because it's the average of the 30th and 31st observation. So on this interval, this only goes up to our 26th observation. So our median must be in here somewhere between 75 and 90 minutes past 9 o'clock. So 75 minutes past 9 o'clock is 10:15. So somewhere between 10:15 and 10:30. All right, I hope these explanations help.